Okay, so this is what the lab looks like. Can everybody see this?
Yeah.
Okay, so it's on probably for Friday. And if
There
you're
was a
looking
news
at
story about a woman.
the PhET pendulum lab, we're gonna have some things that you're gonna wanna make sure right at the beginning that you have set correctly. So I'm gonna go back up here. It tells you at the very beginning of this lab, right? You want everything set up in a certain way when you start. Let me show you a screenshot of that, what it'll look like. First of all, you wanna make sure that when you get there, you mess around at first like they tell you to with the intro and the energy screen, but then when you're ready to do the lab, make sure that you're on the one to the right that's the actual lab. When you're setting it up, you wanna make sure that over here you have your length set at 0.7. It tells you this in the lab. Make sure that you're using a 1 kilogram mass, and make sure you have the Earth's gravity and no friction on. And make sure that you have everything checked. So they'll tell you to check the ruler, the stopwatch, the period timer. You'll check so you can see this energy bar graph. Stopwatch and period timer. The difference between these two is the period timer will actually time. Remember, a period is a time for one repeating motion. So for example, if you pull this back and it swang from here and then back to here again, that would be a period. And so if you push this play button here, it will automatically calculate the period for you, because it's really hard to try to calculate one swing there and back, just like when you actually did your real pendulum lab. And this clock will do that for you. So the first columns in your lab that you're going to be recording data, you're going to be pulling this back at 40 degrees. They tell you to make sure, and they'll show you right here what the angle is. So you're going to pull this back to 40 degrees. And you're going to get the time for when it's right down here and right when it's back up here again. And the easiest way to do that is to actually get the period, which would be there and back. And whatever this time is, this would be a fourth of that. So that would be much easier than trying to stop this right when it gets right here. So it's going to say use this period timer to figure out what the time would be at the bottom right here and when it gets back up to the top here. And then they're going to have you pick any other places in between there to get the time, and for that part you can use this over here, but you'll have to hit this timer and the start stop button at the same time. That shouldn't be too difficult because it doesn't matter where you get the times in here. So I'm going to put up that table again so you can see what I'm talking about. So in this table, you can see the farthest right, obviously the time there is going to be 0. When you get right at the bottom, that's going to be a fourth of your period when you use that period timer clock. Farthest to the left will be half of that. So these three right here you can get with the period timer. Then these points that you pick, you can just hit the start and stop on the stopwatch whenever you want. It can be any positions in there. You're going to graph this though, so make sure these times are all pretty different times, so you have all of these different points to plot on your graph. You're going to be looking at the graphs over here that show potential and kinetic energy. They also show the total amount of energy, and they show thermal, which we're, remember, calling it dissipative. So thermal is the same thing as dissipative. So it's going to be showing you as this swings these amounts of energy over here. And we're going to measure these amounts of energy not in joules, but we're going to measure it in centimeters. So when they say to figure out how much kinetic energy at a certain time, you're going to take this ruler over here and you're going to measure the length of the bar. Let me put a screenshot on here that shows the actual. No, that's not it. So over here you can see in this position right here, it had just a little bit of potential energy. And you can probably imagine why a pendulum has kinetic and potential, because it's swinging above a certain height. So like right up at the top here, it's going to have all potential. It's going to swing down here. It's going to have no height here because the reference point is going to be right here. So it's going to have all kinetic here, back to potential, back to kinetic. So over here, it's going to show you that. So when they say to measure how much energy, we're just going to say that centimeters equals joules, even though it doesn't really. So you're going to take this ruler over here and you're going to measure these bars to get how much kinetic and potential energy you would have for those particular times. So that's what you're going to be putting over in these. So instead of using joules, we're just going to say a centimeter equals a joule. And then you're going to be making an actual line graph. So you'll be making a line graph for kinetic energy versus time. You can imagine that time is going to be your independent. You're going to allow a certain amount of time to go by and your kinetic energy is changing. So you're going to plot that. And then on the same graph, so you're going to make both line graphs on one, just make it a different color or somehow designate it different. You'll do potential energy versus time. So this will be one line graph, but you're going to put two things on that line graph. Any questions so far?
No.
Which ones are independent?
Independent is time.
Okay.
So again, you're allowing a certain amount of time to go by, therefore the kinetic energy is changing or the potential energy is changing. And another thing in this lab, you can see that they use KE. I told you there's lots of different symbols. We've been using EK, so anytime you see KE, same thing, that's kinetic energy. We've been using EG, but PE is what they use in this lab. Another thing I would definitely do, it says to do it in the lab, is to make sure that you see how it has normal down here, normal time and slow time. Absolutely mark this and make sure it's slow time, or it's impossible to get these times. So make sure you hit this slow button, so everything will be slowed down. It'll get the correct time, but it'll be easier to start and stop the stopwatch here when you have to get the data of any other positions in here that you want to get. Let's see what else. I'm just going to scroll through the rest of this lab. So you'll be making your line graph here, and then you're going to use your line graph in number 3 to predict what the kinetic and the gravitational potential energy would be at exactly 0.5 seconds. So on your graph, you'll definitely have 0.5 seconds on there. And of course, all you have to do is go up, hit the line for EK to figure out what it would be, and hit the line for EG for that particular time. Here, right, when they say equation for law of conservation of energy, right, hopefully you understand by now that that can be anything. You're just talking about what would be equal. So for example, in this one, if we started that pendulum up at the top of that swing, we would say the gravitational potential energy is changing into kinetic energy. So in this lab, it's just going to be basically potential energy equals kinetic energy. And then in this problem right here, you're going to assume that 1 centimeter equals 1 joule, right? And you're going to actually try to figure out what the velocity would be, just like you've been doing in those quantitative problems. And then these are just questions about everything that happened, right, that you did earlier. So just remember that anytime they talk about thermal energy, that's dissipative. So dissipative is thermal, sound, all of those things that are really hard to get back. They're calling it thermal in this, but we've been using dissipative. So continue using dissipative in that. Any questions? And again, if you have individual questions when you're doing this, right, just give me an email or a note through Canvas and let me know what you're having questions about. You can see that this is 30, I don't think I wrote it. It's either 35 or 37 points, and the points are after each one here. So make sure you do a good job on this. Shouldn't be too difficult. Questions?
No, not really.
I'm sure you'll probably have some more. Like I said, don't hesitate to email me. What about the worksheets that you've been doing? I'm going to put up the one that was not graded. Just say a couple of things about that. Just make sure when you're doing all of these that if you're doing kinetic energy, you have to make sure that your unit for velocity is in meters per second. So that's why you had to change this 70 miles per hour to meters per second. So they sort of told you that here. Make sure that your masses are in kilograms. So the mass in the kinetic energy and the gravitational potential energy, if they give it to you in grams, you got to change to kilograms. This one is in kilograms, but if it wasn't, you would have to make sure it will not be joules unless you have it in kilograms. Same thing with any length. So for your velocities, for your heights, they have to be in meters. So a lot of people going down to number 4 here did not have the right conversion from grams to kilograms. There's 1,000 grams in a kilogram, so you would have to divide 50 grams by 1,000. That means you would have to move the decimal 3 to the left, so this should have been 0.050 kilograms. But most people are doing really well on the problems, it's just these conversions. And then this one had centimeters, it has to be in meters. So to go to meters, there's 100 centimeters in a meter. This should have been 0.10 meters. So just make sure you're changing your units all to the standard metric units. The other problem that I've been seeing is that in your equations, I guess I didn't write them up here. In your equations for kinetic energy, it's 1/2 mass times velocity squared. A lot of people, when they're putting in their velocities, they're not squaring them. So for example, in this one, right, how fast you're finding the velocity, but in the equation it's velocity squared. So at the very end, you had to take the square root. So make sure you're putting in velocity squared. Same thing with your elastic potential energy. You have to square the displacement. So if this was compressed by 0.1 meters, when you put it into your equation, make sure you put 0.1 meters squared. A lot of people had this wrong just because they did not square the change in position or the displacement. Looks like your energy bar graphs are very good on all of these. This one was a nasty one because we actually did have some energy that went to heat or dissipative energy. So a lot of people had trouble with this one. So your gravitational at the beginning is all going to be converted to kinetic, plus we lost some energy, or didn't lose it, but transferred it to dissipative. So this would be the equation. Gravitational equals the kinetic down at the bottom here, plus any that went to friction or heat due to friction. So when you did this one, a lot of people just did this part right here, and you did not account for this amount that was lost to friction. So really what you'd have to do is say the gravitational potential energy is equal to how much kinetic energy you have down here, plus the amount of dissipative. So how you could figure out the dissipative right here would be, that's going to be 10% or 0.1 of your original amount. Or because if you did think about this as being equal here, you could put 0.1 of this kinetic energy. So either way, you had to take 0.1 and then times m times g times h here to account for that dissipative energy. That's why everybody was just a little bit off if you just did this right here. You got too high of a velocity because you did not account for some of that going to heat. Those are the major problems that I saw, but those are minor problems. So overall, you guys are doing a good job on these. Any other questions about the graded quantitative or the energy bar graphs? There's a lot of people that still need to turn in those problems that are graded for the energy bar graphs. Any questions on either one of those?
I don't think so.
No, not really.
Well, everybody go ahead and turn your, I'm going to stop sharing my screen for